Well, I think we're live here, so thanks for joining in and for another session of FE Civil Review 2022. Tonight we're going to be talking about surveying, where we get to take a look at measurements and stuff and angles and distances. And actually the FE also throws in area computations in here, earthwork volume computations, coordinate systems, and I mean that gets into GIS and that sort of thing, but we'll see how that works there. But what we're going to be doing is jumping in with some of these different questions and going from there. So hopefully this stream is working for you. If you can hear me, that would be awesome. If you could just put a chat in, let me know that things are going okay, and we'll just jump in with some questions here. So hopefully these problems are helping you. If you don't have the most recent, you can go download the problems below. So we're going to jump in with just some really basic things here. So this is kind of a warm-up, but if we're looking at this and we have an angle of 115 degrees, 15 minutes, 24 seconds, and I lost my seconds there, but if this has 114 degrees, 15 minutes, 24 seconds, what is it in decimal degrees? And hopefully you know how to do this on your calculator. If on the TI-36X Pro, the one that I use, this is in the calculator, so you can go under math, specifically under the math button. There's a DMS, degrees, minutes, seconds. You can go there and you can enter this right into that and actually just hit enter, and it'll tell you what the decimal degrees are. But I also want to just kind of go through the conversion here just for fun, just because sometimes it's useful to understand the conversion. But if we have the 114 degrees, that's not going to change. 114 degrees is going to be 114 degrees, and you'll notice these all have 114 degrees. So that doesn't really help us, but what's 15 minutes, right? 15 minutes times what? Times for every minute, for every 60 minutes we have 1 degree, and that's going to give us, actually I don't even know what that's going to give us, but basically what we're doing here is we're adding 114 degrees plus 15 minutes times 1 degree per 60 seconds, and then adding also the 24 seconds times 1 degree per 3600 seconds. So 60 times 60, 60 minutes, 60 seconds. You put all that in, and you should get an answer here that matches one of the ones on the side. So 114 plus 15 over 60 plus 24 over 3600 is going to be like 114.2567, 67. And did I round wrong? I must have rounded wrong. So or no, it's 667. Yeah, it's probably 67. So anyway, I think I must have rounded wrong in the first one or something. But let's look. Actually, let me just put it in the calculator, see what happens too. So if I put this into the calculator, do 114, and then if you press the math button, go over to degrees, minutes, seconds, you can add the degree symbol. 15, again, math, degrees, minutes, seconds, minutes, and 24 math, degrees, minutes, seconds, all the way down to seconds. So you hit enter and you get the same thing, 25, 67. So man, I should know how to round, but anyway, this is the answer that we're going to go with, and go from there. So hopefully that makes a little bit of sense, and let's just keep going. So again, if you're on the TI-36X Pro, which is the one I'm using, I don't know, maybe you can put in the chat what you're using. Some people like the Casio version, some people like the HP, but for me, this is what I'm using. If you go to math and then to DMS, you can get degrees, minutes, seconds, and just enter this in directly, and once you hit enter, you get the conversion as well. So kind of a simple problem to jump into, but I managed to, that 1,000, whatever, it's the 10,000th is bugging me, so we'll just keep moving on. So let's go to this one, angles, distances, and trigonometry still. We have a survey control point, and a lot of times with surveying, you're setting up control points, you're setting up, maybe doing a closed traverse and setting these fixed points in the ground that you know where they are, so that you can kind of reference everything off of those points. And here we have a control point at point A. So I'm just going to draw a point down here. This is point A, right? So what do we have? This is point A, and the northing on it is 1,000, and the easting is 1,000 as well. So I just picked kind of an arbitrary value here. Sometimes if you're not referencing state plane system, you might just be, pick an arbitrary value. So I'm picking this point, and I'm going to say we have a bearing, of course, AB. And point B specifically is going to be over at north, 1230.30 and east, 1476.59. So what I'm going to do is I'm just going to plot that, right? So I'm going to plot that point, and what's this going to look like? So if every, couple blocks is 100, let me come over here, and maybe what I'm going to do is I'm going to come over to 1476.59. So maybe this is like my 76 point, and then I'm going to come up 230 or so. So that's going to put me at some point maybe around here. Okay, so this is going to be point B, and my course is going to go connect those two, right? This is going to be course AB. So the question is, what is the bearing of that course? Now, typically on like property surveys, that type of thing, you're going to have a bearing which has an angle and a distance. This can be known as the meets and bounds of that survey, and that will show up. It'll be what is the actual description of the survey. Typically, there will be courses and points that will be gone from and to. So the question is, we have two things. We have to figure out the angle, and we have to figure out the distance. So the distance should be the easy part. Let's start with the easy part. Well, hopefully they're both fairly straightforward as well. But let's look. The northing we said was 1230.30, right? The easting was 1476.59. So what does that mean? That means we have a certain distance, right? We have a certain distance here of east 476.59 feet. Okay, does that make sense? So I just subtracted the one coordinate from the other coordinate, and I just got that distance. And similarly, we're going to have a distance, vertical distance here of 230.30 feet. Okay, so nothing too crazy. But once we have that, the distance of this bearing should be pretty straightforward, right? So the distance is just going to be, what are we going to say? The distance of AB is just going to equal the square root of 476.59 squared plus 230.30 squared. Okay, so this is just Pythagorean's theorem. We're solving for a distance here. And if I do that, hopefully I didn't screw this one up, but 476.59 squared plus 230.30 squared, I got like 529.32. So this is good. So that's equal to 529.32 feet. So we can cross out a couple of these. And now we're just looking at the angle. So the question is, it's not so much a question of what the angle is. These angles are pretty far apart. 25 and 64 are pretty far apart. Okay, but I guess the question is, which angle is it, right? When we're measuring bearings, how do we measure those? And typically, the angle that we're going to measure here is going to be, from the north point down to the east. Okay, so we know that we're going north to east, so we're going to measure this angle. I'm going to call this angle, maybe let's just call it phi. Right, and if I get that angle, I should be able to solve this. So if I do some basic kind of algebra here, or I'm sorry, trig here. So tan phi is going to equal what? Well, this is the opposite over the adjacent, right? Which is going to equal 476.59, right? Divided by 230.30. And when we're all done, we get phi equal to what's that? Well, let's just do it and make sure I didn't screw this one up. So tan inverse of 476.59 divided by 230.30. That gets me to about 64.2. I said it right. 2090. Okay, 64.2090 degrees. Which does, this is going to match our value here. But again, if you want to go 2 degrees minutes seconds, if we want to go 2 degrees minutes seconds, I can just hit math, right? So in my TI 36X Pro, I'm just going to hit math. I'm going to go over to DMS, And then under degrees, minutes, seconds, right? So if I come all the way over there, if I go down all the way to the bottom, number 6 is, number 6 here is going to be a little triangle in DMS. This will actually convert to degrees, minutes, seconds. So if I put that in, I actually get a converted value equal to 64 degrees, 12 minutes, 32.49 seconds. I mean, it'll actually be 4903 in the calculator. So the question is, always from the north, or could it be from the south? Yeah, so actually that's a really good question, because this angle is measured either from the north or the south. So the first value is going to be the north or the south, and if this bearing was to the west, for example, it would be north some angle, angle phi1 or whatever we want to call it, west. So if it was going to the west, we'd have to deal with it that way. If we were starting from the south, we would deal with it from the south as well. So we could have a south bearing, or if we were going from or if we were going from B to A. So if we were going from B to A, for example, right? If we're going so the bearing from B to A would have the reverse angle as well, because now we'd measure. Let me just draw B to A over here. So B to A would be like this, right? So if we had B up here and A down here, now we're measuring from the south over to the west. Does that make sense? So it's the same angle, but B to A would be south 64 degrees, 12 minutes. 12 minutes, 32 seconds west. Okay, so the south and the west and the east, or the north and the east, get flipped if we're dealing with it, in the reverse direction. All right. So the bearings are a little bit confusing, but that's why a traverse will typically have a direction too. So if you're looking at a traverse, there's going to be a direction of travel, which way you're going, so that you know kind of which way to turn your angles. So that should make some sense. Okay, but just some of these basics with angles and how they're measured in surveying, because they're a little bit different in the sense of you're looking at points and coordinates on a bigger plane versus maybe a vector, and you're looking at these meets and bounds, which have decimal degrees, and that's gonna make a little bit of a difference. Okay. So just some of the basics here: angles, distance, trig, and honestly, if you know some of those basics, it's gonna be able to help you get through surveying. Honestly, it really will. So hopefully that one makes a little bit of sense. All right, let's keep going to question 3. Question 3 is kind of the idea of a closed traverse. Again, typically in surveying, what you're going to do is you're going to lay out some control points around either a building or something that you're surveying, right? So you're surveying an area, you're going to lay out these control points, and then you're going to use those points as reference points. And one of the things that you're going to do is you're going to correct the coordinates for those points. So in any survey, there's going to be some error, right? And what you want to do is you want to correct that error and minimize the error, but also distribute the error appropriately to the different points. So with this, what we have is essentially 3 control points. This is a small survey, but this table here gives information obtained by a closed traverse using the compass rule. And this rule doesn't really show up so much in the FE reference handbook. Okay, so if I don't know if this would be shown on the FE or not, but I wanted to go through it because when I taught a surveying course, this was just one of those things where we did a closed traverse. We wanted to minimize error. One of the things that does show up in the reference handbook are latitudes and departures. So this was kind of where my mind went when I started thinking about latitudes and departures, specifically in the reference handbook. So in the reference handbook, there's one page on surveying, and that surveying page doesn't even say surveying at the top, right? So it's like surveying's like a second cousin that just almost got invited to the party. But here we have latitudes and departures. That doesn't even say surveying, right? And specifically, the latitude goes up and down, the departure goes left and right here. So it's one of those things. We'll look at that with this problem. But the surveying part of this is just some earthwork formulas, really not that much, right? So some of the stuff you just have to know and to hopefully remember from like your sophomore year when you maybe took a surveying class, and hopefully it makes some sense. But what we're going to do is we're going to work through these latitudes and departures, and hopefully they'll make a little bit of sense. But what we're going to do is we're going to have a few different points. So we're going to start out with like point A, for example. So if this is point A, our traverse has these measurements. So we know we have a distance of 95.49, but we don't have an angle. What we have here is a latitude and departure that were calculated, right? So the latitude is going to be 82.62. If you remember, the latitude is up and down. So I'm going to come down 82.62. So I'm going to come down, I'm just going to sort of eye this in, 82.62. So the negative means down. Right, so I'm going to go down, and then I'm going to go left because I have a negative 47.88. I'm just drawing this out. You don't have to draw this out. If you get a question like this, you don't have to draw it out, but just like a good free body diagram helps you, I think a good diagram will help you if you have some sort of a closed traverse, right? So here we have this, that distance of 95.49. You could, would be this straight distance. Okay. So we got our latitude, our departure, and then we go, so this is from point A to point B. Okay, so this is point B. And then what do we do next? We go from B to C. So from B to C, we have a latitude of 32.17, and that's down again. So we're going to come down, 32.17, so it's about here, and a departure of 82.49. So we're going to come to the right, 82.49. And I'm trying to keep this somewhat to scale, so it's going to come over, maybe about there. So this is, minus 32.17 and plus 82.94. Okay, that brings us to point C. And in a perfect world, what would happen is the last latitude and departure would bring us right back to A. So we'd come, up 115.12, and then we'd come back to the left here, 34.79. Okay, so this is kind of like the perfect world scenario where everything works perfectly, but everything's not perfect, because if we take a look at this and I sum my latitudes, what do I get? Right, so if I take that minus 82.62, so I'm just gonna sum this column, right? So if I sum this column, I'll get an answer down here, minus 82.62 minus 32.17 plus 115.12, and I got a difference here of 0.33 feet. So that means we took all our measurements, we went all around the circle, we ended at the same point we started with, and if in a perfect world that error would be 0, but we're off 0.33 feet. Is that a lot? Well, it's not great, but it's okay. So what we're going to do next is we're going to do the same thing with the departures. So I'm going to sum these departures up, and let's see what we get. So I get minus 47.88 plus 82.94 plus negative 34.79, and I get 0.27 feet. Okay. So the question is, how do we, split this up? And this is where the compass rule kind of comes in. And this is just kind of like a weighted average type thing. So we're just going to weight this based on the length of the course. So the bigger course length gets more error. Does that make sense? So we're going to use, essentially, we're going to use these horizontal distances to kind of weight the latitudes and departures. And the way that I like to do that is typically in a spreadsheet, but on the FE, you don't have spreadsheets. You have paper or a marker and a whiteboard. So what I like to do here is I'm gonna write down a couple things. I'm gonna write a new table that has maybe I'll write it here so we have a little bit of more room. Maybe I will write it. Maybe I'll write it here. I'll write a correction. I'll write a line for corrections. Okay, so we'll have a corrected latitude, or a correction for the latitude, a correction for the departure. And then what we'll have as well, in addition to that, is we'll have a corrected latitude and departure. And we'll use these corrected latitude and departures to get our actual coordinates. Okay, so how do we get the corrections, or how do we get the corrected latitude and departure? Well, for point A up here, what we're going to do, let's just look at point A, right? What we're going to do is we're going to say I'm going to take this 95.49, and I'm going to multiply it, or I'm going to actually let me take a step back. Before I take that, let me just take a step back here. The other thing that I want to do is okay. So let me start over. In order to correct these, I'm going to weight these departures, how much we split this, based on these lengths. I kind of said that, and what we're going to do here is we're gonna weight this based on these lengths. So what I'm going to do is I'm going to take the 95.49 and I'm going to divide it by the sum of all the lengths. Okay, so let me actually come back here, and I'm going to move this over a little bit, just to see where we can get to a little bit more room here. But I'm going to sum the horizontal distances. So sum of HD. I'm gonna look at that first. So if I add all these up, I'm going to get 95.49 plus 88.96 plus 120.26. I got 304.71. And now what I'm going to do is I'm going to take these corrections and apply them based on the actual horizontal distance. So for point A, I have a horizontal distance of 95.49. In the factor that I'm going to use, I'm going to divide that by like 304.71. Okay, so this is sort of like the gravity model in transportation. It's sort of like moment distribution, where you're coming up with like the Hardy-Cross method. You're coming up with points here, or factors to kind of distribute this based on some parameter. And then I'm going to multiply this by either 0.33 or the 0.27. So awesome. I'm glad you felt good. I hope that these reviews are helping you guys, and hopefully they're not screwing you up. Just keep practicing, keep working hard on this stuff. It's gonna help. But if I plug this stuff in here to the calculator, what am I gonna get? I'm gonna get like about 0.10. So the correction is going to be 0.10, but what we have to think for a second is, wait a second, we're 0.33 over here, so we actually have to subtract this off, right? We have to say minus 0.10 for our correction. So does that make sense? So we're 0.33 above or too much, so we're going to subtract that to get it back down. We can keep doing this, but I'm going to, this is the correction for the latitude. Similarly, we're going to correct the departure, 95.49 over 304.71 times 0.27, and what do I get? I get 0.08. I get 4.6. I'm just going to leave it at 0.08. Okay, so again, I'm going to subtract this off, minus 0.08. And if I kept going here, I'd get another minus 0.10. I'd get a minus 0.08 here as well. These distances are pretty close to each other. This distance is a little bit bigger, so we'd expect a little bit more error to go to that one, and I get like a minus 0.13 and minus 0.11. Okay, so those are the corrections, and now the corrected latitudes and departures. All we're going to do is we're going to take the 82.62 and add this negative 0.10 to it. So I'm going to get negative 82.72, and my corrected departure is going to be negative 47.8, and 8 is going to be, what's that, 96. Okay, so these are the new latitudes and departures. So in other words, instead of coming down 82.62, I'm actually coming down 82.72 when it's corrected. Instead of being 47.88, I'm actually 47.96. So what does that mean? That means when I go from point A down to point B, right? So this is the coordinates of point B. So the coordinates of point B are going to be what? It's going to be, well, the northing is going to be 1000 minus the 82.72, that corrected value, right? So if I do that, 1000 minus 82.72, I got 917.28, which is one of the numbers up above. So I'm feeling a little bit good about this. Let's just double check, make sure our easting is good before we just circle the answer, but we subtract off this 47. 0.96, and hopefully we get the second half of that answer there, 952.04 feet. Okay, so this gets us an answer that we're kind of happy with. Okay, so hopefully this makes a little bit of sense here, right? But the whole idea with the compass rule is we're trying to correct this. We're trying to take that error and we're trying to bring it back to 0, so that when we set up, on point A or point B or point C, we kind of know where they are, and we can use those to reference other angles. So we'll do that later on in the course of this. Actually, the next question is kind of one of those. So I kind of blew this question on the transpose section, so I had to resurrect it somehow and bring it back to life a little bit. So so awesome to hear that this has been helpful, and I really hope that it is. I mean, honestly, I'm only doing one review for one session, but hopefully these sessions are helping you, and hopefully you can find additional resources to get more practice problems, because the more practice you can do, the better off, honestly, I think you'll be. But hopefully this kind of gives you an overview of what's going to be there, and kind of just trying to hit all these major topics, right? So I'm just going through each topic here, trying to hit every topic and kind of give you my thoughts for what's going to be what's going to be important to know. So would you get a compass rule correction problem? I don't know, but maybe you could get something that has to do with closure, or maybe you get something to do that has to do with error, or something along those lines, that where this problem's a little bit longer, but it's not super crazy, and I think it's a doable problem. So but if you don't remember the compass rule, you might end up with one of these other answers. So I think I put some of these answers in there where if you don't correct it right, or if you don't correct it based on kind of the weighted distances here, it might not work out the same. Okay, so let's go to question 4 here. And again, this is distances, angles, trig, but what do surveyors do? Surveyors lay out construction, right? I mean, that's they measure as-built conditions, they measure existing conditions, but they also lay out construction. So I just wanted to resurrect curves here for a second and say that we have a surveyor that's tasked with laying out a horizontal curve. So we have a radius of 500 feet, and we've got a couple other things going on here. So I'm just going to draw my curve in here. So we got a radius of 500 feet. We got a circle here. What we know is we've got some tangent that comes in, right? Some curve and some tangent that goes out. Okay, so this is our curve. We've got a radius of 500 feet. I think the problem says that there's an angle of 40 degrees. This is our point of curvature here. Our point of tangency is here. And if we extend this point out and extend this point out, we're going to have a point of intersection somewhere out here. So the question that this asks is, okay, so we have this alignment kind of already. So this alignment's been established, and that's good. We went all the way out to our point of intersection. We're backsighting. We established our point of curvature. And now the surveyor is going to set up right on this point. So the surveyor is going to set up on this point, and he's going to try here, she's going to try to lay out the point of tangency. So the surveyor wants to, take a shot here and lay this point out, both in terms of the length and in terms of the stationing. So what are we going to do? So typically what the surveyor will do is they'll foresight onto a known point, like a traverse point or a point of intersection. They'll take a shot there and zero out their angle. So this is their reference angle, and this is where everything else is going to get turned from. Okay, so this might be the reference angle. And then what we have to do is we have to turn a certain distance and a certain length. So the question says, the station chord length and angle that would need to be turned from the PI to the PT required to lay out this curve are most nearly. So what we're trying to find here is we're trying to find essentially this angle that needs to be turned. We're trying to find this length that needs to be shot, and we're trying to find what the station is at the PT. Okay, so let's just walk through each of those kind of in turn. And would you get all three of these? Probably not like this on one question, but I wanted to hit each of these just in turn, just to make sure that they make a little sense. So I'm going to start with I'm just going to kind of work from left to right here. So the PT, what is the PT? Well, this is where I was responding to a question kind of off the cuff, and I just wasn't thinking. And this is where some of these equations get so weird. But the point of tangency equals what? It equals the PC plus, what do we want to do? Basically, we want to measure along the distance of the curve, right? So when this curve's getting laid out, you're measuring out to the point of intersection, then you're backsiding to the PC a distance of t, right? So this is that t, and we did that question in the transpose section. But then to get to the PC, what we're going to do is we're actually going to add the length of this curve. So we're going to add L. So L is, maybe I'll do another color in here. L is that length of the curve, right? That's the length of the curve, the arc length. Okay, so that's going to get us to the station here. And we're told, what are we told? We're told the PC is a 10 plus 0, 0. So we need to find L. Once we find L, we can find the point of tangency. So let's come back to the FE reference handbook. And this is where you might be in the surveying section, but that's okay. You actually have to come back to the horizontal curves here that are in the transportation section, right? So transportation section, horizontal curves, and we kind of did this question, I think, on the transpose section, but L is what? Ri times pi over 180. So let's get that back in here. So let me, solve for L. So L equals Ri times pi over 180, and that's going to equal 500 feet times I, this angle 40 degrees, okay, times, to go from degrees to radians, divided by 180. So this is just like a fraction of the diameter, essentially, right? So this is just a fraction of the diameter. And what do we get? We get 500 times 40 times pi divided by 180. And I got like 349 feet. So what's the PC? The PC, we're going to add, to essentially, what, 1,000 plus 349, right? So to go from stations to feet, we just multiply by 100. 10 stations times 100 is going to be 1,000 feet. And this is going to equal about 1349 feet, or it's going to equal 13 plus 49. Okay. So the good news is we can cross out a couple, right? We can cross out the 1342s, and we're left with a couple of answers here. So now you kind of pick your poison. What do you want to do, the LC or the angle? And maybe you can just look at this and know what the angle is. But what I'm going to do here is I'm going to do both of them, just because we want to learn. We don't, like on the FE, if you see a problem like this, you're going to pick the easiest thing to do and just do it and be done with it and move on. Unless you have extra time on your hands and you're just like, well, I want to double check that, like, who knows, maybe you have extra time, but normally in the FE you'd be coming up with a strategy to kind of do the quickest thing. What can I do that's quickest? But here, let's go and find LC. This is that chord length, right? This is the chord length here that we're trying to find. So let's look at this. This is LC, and what do we get? We get LC. Let's go back to our formulas here and figure out where that is. So if I come down, do I come down? No, I come back up, right? LC, we can get from this formula, LC equals R times 2 sine I over 2, right? So I'm just rewriting this equation. You got to find the equation that works, but LC is the chord length. That's this horizontal kind of straight line distance that we're gonna sight in with our survey instrument to make sure that we can get there. So let me write that in here and we can take a look at that. But what we know is LC equals R times 2 sine I over 2. And what do we get? So 500 feet times 2 times sine of 40 over 2 is going to equal 500 times 2 times, let me put this in my calculator here, 40 over 2 is 20. So I got like 342 feet. So that's that straight line distance that needs to get laid out. So good news is we got an answer here. We got 1349 and 342. Let's just take a look at that angle real quick to make sure that we're happy with the angle. Okay, so what does that angle look like? let's just take a look. So 3 is the angle. And to look at that angle, I'm just going to come back up here for a second, because what we see here is we have this chord length that's perpendicular to this line coming in, right? So these two lines are perpendicular. If those are perpendicular, this is going to help us, because what that does, it gives us kind of a reference here, right? So we have, you know, the one line, you know, coming out. We got the other line that's perpendicular, right? And then if we keep turning, right? If we keep turning this, what do we know? We have this other line down here and another line right here, right? So these are the various pieces that we have. So this is our 40-degree angle. This is our 90-degree angle, right? And where are we going from? We're going from PC down to PT, right? And we should know, because this, you know, this is tangent here as well, right? Because this is 90 degrees as well. We should be able to figure something out here. This is an isosceles triangle, right? So what are these two angles? Well, what's left? It's going to be 180 minus, you know, so this angle, let me just call it alpha, right? What's this angle? This angle alpha. Alpha equals 180 degrees. That's for the triangle, minus 40 degrees, right? Times 1/2, right? So basically we're gonna, does that make sense? If you add up alpha, right? Alpha plus 40 degrees, that has to equal 180 degrees. So this is just basic geometry, right? So what we get here is alpha equals to 70 degrees, right? So 140 divided by 2 is going to be 70 degrees. So if we keep projecting this line, right, this tangent line, that means we have a new angle here. Let me call this one beta, right? And beta is just going to equal 90 degrees minus alpha equals beta. You see it? So just some basic geometry here, but I wanted to throw that in there because sometimes there's not like a formula necessarily. Like if you look at, you know, you could come here and say like, wait, there's this angle here, there's this angle here, there's no angle here. How do I get that angle? But if you take a step back and think like, wait a minute, this is an isosceles triangle. This is the radius, this is the radius, and you know, this is a chord length. We should be able to solve it, right? So this just goes back to some of those first things that you learned in like, you know, 9th grade geometry or whenever you took geometry, right? But basically you're gonna get a beta angle here of 20 degrees. Okay, and maybe you knew that before me even saying this, but at least we double checked it, made sure, and it works. Okay, so again, some of these basics here, but the point of tangency is the point of curvature plus the length, whereas this PC is pi minus t. Okay, so I just wanted to make that you know, make that work. So if you have questions, let me know. But hopefully this is working for you. So Austin, hopefully I didn't screw you up on that if you took the test yesterday. But if you're still on, I don't know if you're still on or not. But if you do pass, you know, reach out, let me know. I'd love to hear from you. Love to hear, and that goes for any of you else that are taking this thing. If you do pass, definitely reach out. Let me know. I'd love to celebrate with you, congratulate you, and wish you the best. So hopefully we can talk later. So let's keep going. Question 5. Coordinates of an irregularly shaped plot are shown below. The area of the plot is most nearly. So we have a plot, we've got some distances, we've got some things going on. This is one of those things where we've jumped from angles, trig, and distance right now to area comps. Area computations are just some different ways of finding areas and volumes that we should be able to do without too much trouble. But this is one of those formulas that is in the reference handbook that I personally don't like. I just don't like it. And the reason I don't like it is because when I taught surveying, I didn't teach it this way. I'm just going to tell you, I didn't teach it this way because there's an easier way for me to remember it. And this formula gets confusing with the B's and the N's and the C's and the A's, and there's just a lot of letters going on in there. Okay, and you can use this formula, but if you get a problem like this, I'm going to show you a way that I think is easier. Okay, so if you're doing area by coordinates, what I would suggest that you do is you write out your points in a way that looks like this. So in a way that looks like, you know, let's put it this way. You do essentially like an x over y. Okay, so you write out each point in this format, x over y. So I'm just going to start, you know, in this bottom corner, 700 over 100. So I'm just going to write these out, 700, you know, over 100. This isn't a fraction. It's just a way of remembering how to do this type of a problem. So this is where I'm going to start. I'm going to write that out, point 1. I'm going to go to my next point, which is, what, 1,000 over 200. I'm going to go to my next point, 900 over 450. I'm going to go to my next point, 700 over 300. And don't forget, you got to close this thing and come back to the last point, 700 over 100. So after I write all these points down, essentially what you see here is area by coordinates. We're multiplying an x value by some kind of y value and some difference between two y values. The way that I like to do it is, you see how this is xa and yb? What I suggest here, and one way you might be able to remember it, is just like the xa times yb, right? So what we're going to do is we're going to take the first x and multiply it by the second y. You see that? And then so I'm going to write this down. I'm going to write 700 times 200, and then I'm going to add to that. I'm going to add to that 1,000 times 450, and I'm just going to keep going. I'm going to add to that. I'm going to say 900 times 300. Okay, and one more time, I'm going to close this off here. I'm going to add in 700 times 100. So this is kind of like a first pass, right? It's kind of like xa times yb. Okay, if you think of it like that, right? So this is a first pass, and I can calculate that out, and I can get some value, right? So if I calculated that all out, when I did it ahead of time, the number that I got was 930,000, essentially feet squared. Okay, so this is just a big number of feet squared. That's not our final answer, but it's an answer that we need to kind of keep going. Because the second thing that we want to do is we want to take a look back here, and if we come back to this formula for a second, what do we see? We see yn, so the last y times the first a, or you know what we have is ya times yb. Do you see that ya times yb? So what that looks like here is essentially what we're going to do is I'm just going to change colors here, but I'm going to take the ya times xb. So this is kind of like the second pass, right? I'm going to take ya times xb, okay? And then I'm just going to keep going. So what's that? It's going to be 100 times 1,000 plus 200 times 900 plus 450 times 700 plus 300 times 700. Okay, so I'm just following these, and I'm just following from kind of the bottom to the top, the first y times the second x. Okay, so I'm just doing this out, and I get a number here of 805,000 square feet. And if we come back to the formula here, we see something else. We see that we have to subtract these, right? So we're subtracting this essentially, right? So what I'm going to do is essentially I'm going to come back here. I'm going to say the area is going to equal, the total area is going to equal, kind of basically what we're going to do is we're going to take the first pass, and then what we're going to do is we're going to subtract off the second pass, right? And if we come back to our formula one more time here, you see that it gets divided by 2. So we have to come back and we have to divide all of this by 2. So we get a value here of 930, 1,000 minus 805,000 divided by 2, and this is going to be feet squared. And we get an area equal to, let me just double check, but I think that's 125. So 903,000 minus 805,000 divided by 2. I got like, or what did I do? No, I put it in wrong. 930. Okay, so 930. Yeah, so I get 125,000 feet squared divided by 2, which is going to be 62,500 feet squared. Okay, so I like to, you know, I'm not a huge fan of this formula, but I like to apply it this way. When I taught this stuff, that's the way that I did it, because I find it to be easier to remember how to do it that way. It's just a kind of a method to do it. But the problem is we have acres. So maybe you don't remember what an acre is. I was actually looking. Maybe somebody can tell me. I know there are some English to metric conversions on the TI-36X Pro, but I didn't find any, like, I didn't find the constant. Maybe the constant's in there, or the constant that I was looking for wasn't in there. They have some constants built into this thing, but I wasn't finding the constant. So the question is, you know, where does that show up? How do we find it? Right? They have some like speed and light and gravitational acceleration constants. They have got all sorts of things for physics in the constant section, but I didn't see area. So maybe you don't remember what an acre is. That's okay. There's a control find here, and I did this kind of right before we started, but to make sure that it wasn't there. There's an acre day. There's an acre. It's 43560 square feet. Okay, so if you don't remember that, you should be able to get there. 43560 square feet. I'm just going to come back here so we're in the right spot for later. And sometimes getting back and forth can be a challenge, but hopefully it makes little sense. So we're going to multiply this value now times, for every 1 acre, we have 43560 square feet. And we're going to get, basically just divide by 43560, and if I can type it in right, that'll be 100% helpful. But I get 1.43 acres. So I get 1.43 acres. Okay. But I really like, this approach here where we're solving kind of with it's an easier way of, in my opinion, of looking at this, of doing the area by coordinates, but it takes some of these irregular shapes and makes it possible. But also that conversion for acres is something that I think could 100% show up. It's in the reference handbook. It's not like it's a mystery that 1 acre is 43,560 square feet. Maybe that's just the number you stick in your head, but it's one of those things that I could see showing up on the test. So area by coordinates. So the next couple of problems, actually, I did in a way where we're kind of going to do the same problem twice, and I hate to do. Oh, good, Sammy. I'm glad you like that way. But I'm these next two problems. If we look at problem 6 and we look at problem 7, you'll see we have swale cuts, right? And these could be swale cuts. They could be road cuts or road fill. They could either be road cuts, swale cuts, road fill, that type of thing. But they're prismoidal sections. They're trapezoidal sections, right? And we're going to look at these with two different formulas. So one of the reasons I wanted to do this is because there's so few formulas in the surveying section. I just wanted to make sure you understood how to use them. So we've got the average end area formula and the prismoidal formula. I was talking to somebody yesterday and he said, we never learned the prismoidal formula. I said, okay, it's not hard. You can do it, believe me. If you know how to do some basics, you can do it. So the average end area formula is just like it sounds. So this question, we have a 200-foot long swale. We have to cut it, right? And it uniformly increases in size, kind of from this 1 foot to 1'6", and a depth here 1 foot to 1 foot. So it increases in depth, it increases in size, and we want to find the total cut using the average end area formula, or average end area method, right? So what are we going to do? We're going to take a look at that formula, but let's take a look at the formula. What's the formula say? It says the length times A1 plus A2 over 2. So really kind of a basic formula here. But basically the volume equals the length times A1 plus A2 over 2. So we're just taking this average and areas, right? And what we're going to do here is we're going to say maybe we can make this area here. This is our cut. I'll make it red because cut is often red and fill is often green. Okay, so I'll make this red. So this is our cut here. We're going to have another cut here. right? And we have to find essentially these areas. Okay, so the areas shouldn't be too much of a problem. I'm going to call this area, 1, or sometimes you can label it by the station. But area 1 equals what? It's going to equal 1/2 of the average width of this, which is going to be 5 feet plus 1 foot, right? And then it's going to be times the height, so times 1 foot. Does that make sense? So it's the average width, so 5 feet and 1 foot. That's 6 feet over 2 is 3 feet. 3 feet times 1 foot is going to be 3 feet squared. So 3 square feet. Okay. And we can do the same thing with this. We can say that area 2 is going to equal 1/2 of, what's this, 7.5 feet plus 1.5 feet times a depth of 1.5 feet. And I don't like my 1/2 there. It looks sort of funny. So that looks a little bit better. And we do this, we get, 9 divided by 2 is going to be 4.5. 4.5 times 1.5 is going to be like 6.75 square feet. Okay, so pretty basic, just finding an area of a trapezoid. And now we know that we're going from station 10 plus 0 to 0, 12 plus 0, 0. So that's 200 feet. So we're going to have a 200 foot cut here. We're going to take, the average end areas, which is going to be 3 square feet plus 6.75 square feet divided by 2. And we're going to get a value that we hope is good, right? But the problem is if you read the problem closely, you realize that, well, there's 2 problems. One, we get 975 cubic feet, and you sort of think for a second, wait, that doesn't show up above. That's so Madison, you screwed something up. And I screw a lot of things up, but I didn't screw this one up. The thing that I asked for here specifically was in cubic yards. So a lot of times you have to be careful too, especially I noticed in the FE, kind of like the NCEES sample problems that they publish, they a lot of times put the units in the problem, not on the answers. So you got to be careful with that. So definitely pay attention to the units, and you got to remember here, well, what's a cubic yard? A cubic yard is, do you remember? 27 cubic feet, right? So it's just a box that is, it's 3 feet by 3 feet by 3 feet, right? So that's a cubic yard. So that's 27 cubic feet, right? Or I could do F feet cubed. Okay, so when we do that out, we divide by 27, and I got like 36.11 cubic yards. Okay, so I'm going to take my 36 and be happy. All right, so average end area formula, not super crazy, pretty simple to do. You just have to find a couple areas, multiply a couple things, and you get an answer. But you got to remember sometimes those conversions to cubic feet to cubic yards, because typically when you're looking at cut, you're doing measurements in cubic yards, not in cubic feet. Okay. So the next question, almost identical question, but the only difference here, I say the only difference, there's 2 differences. One, we get this extra section at station 11, and 2, we're told to use the Trapezoidal formula. Okay, and I don't know if they're going to tell you on the test which one to use, or if they're just going to say use one or the other. I honestly don't know, but what we'll see here is we actually get different results. So we already know a couple things. We already know this area, right? We already know this area. We did this area was this didn't change. This is area 1. This equals 3 square feet. Okay, I'm going to call this next area down here, I'm going to call this area instead. I'm going to call this area 3 now, but it's the same area. So area 3 is going to be, I think we had 6.75 square feet. So the new area that we need to find is this area here, and this is, I'm going to call this area 2 for now, just because we have 3 areas, so I'm going to make this one the number 2. Okay, but what's this? This is going to be 6.25 feet, plus 1.25 feet all over 2, and we got to multiply that by 1.25 feet to get the total area. So 6.25 plus 1.25, that's 7.5 divided by 2 times 1.25 was 4.6875. So hopefully I did that right. And then the Prismoidal formula really isn't that bad. It's just something that we have to evaluate. And the first time I remember somebody telling me that the average end area formula wasn't actually correct, I had to go double check them. So I think when somebody first said that to me, I was like, "What? You really?" It was a while ago, but I think I built something in CAD even. And I was like a 3-dimensional thing, and I built it and I checked it. So here's the Prismoidal formula. Right, this is length times A1 plus 4 times A middle plus A2. So I guess maybe I should have left that A2 and called this A middle. Maybe I'll change that here. This is let's make this A middle and let's leave this A2 from up above. Right, and our formula goes our volume equals A1 plus 4 times A middle plus A2. Right, that's going to be multiplied by the length, and we're not dividing by 2 anymore. We're dividing by 6. Okay, so we're dividing by 6. So I'm just going to put this over 6 like this. So again, not a crazy formula. It's a lot of plug and chug here. What do we get? We get 3, square feet plus 4 times 4.6875 square feet. Plus area 2, which is 6.75 square feet, divided by 6, right? And the 6 makes a little bit of sense if we think about it, because we've got 1 area 1, we've got 4 of the middles, and 1 of the area 2. So it's a weighted average, but we've got 6 total, right? 6 total pieces, so we're dividing by 6, and we need to multiply that by our 200 feet still, because we're still at station 10. Station 12 is still 200 feet. We're adding this middle station in there for a better estimate of our volume. So if we do this, we're gonna get a volume of, what did I get? I think I got like 950 cubic feet. Okay, so slightly different. It's and if we multiply that times what? Times 1 cubic yard per 27 cubic feet. Right, we're going to get slightly less. So if I get 950 divided by 27, I actually get like 35.119, 35.2 cubic yards, which is different, right? And the reason I wanted to show you these two questions is to show you that these two formulas actually give different estimates. Which one's right? Well, actually, if you actually have a truly prismoidal form section. So if you put this into CAD and start with section 1 and end with section this section at the bottom here, you're gonna actually get this value. This prismoidal form is actually a little bit more accurate. It's a little bit more work because you have another area to find. But in reality, are you gonna have perfectly symmetric sections? Well, probably not. Is it okay to have a little bit extra fill? Yeah, it's okay. So is the average end area method a good estimate? Sure, it's a good estimate. Is it as precise? No, it's not as precise. Okay, so I wanted to show you that because there are two formulas that get thrown in there. Could one of them be on there? Sure, I wouldn't be surprised, but I didn't want to just do one and neglect the other one, and hope that you only get one and that I guessed right. But because there's two formulas in there, I mean, it's easy enough to show the difference. And it's kind of a simple-ish problem that if you get something like this, hopefully you can just nail it and get it right and get the points and move on. Okay? But it is good to know the two different formulas. All right, so we're going to keep moving, and these next two problems are actually similar type things. So similar type thing, we have distance and we have distance. So two, same area here. So I'm just jumping back and forth. We question 8 and question 9. Same formula, or I'm sorry, same area here. But for the first one, we're going to use the trapezoidal rule. The second one, we're going to use Simpson's rule. So are you really ever going to use this in real life? Probably not. You're going to put this into CAD and just measure it, right? I mean, you're going to do an area in CAD or MicroStation and just measure it. And honestly, that's what I've done in real life. But these formulas show up on the FE reference handbook, so I didn't want to neglect them and not show them. I mean, there's like 5 formulas here, so we might as well do a couple problems on each of them. So what do we get? We're going to start with the trapezoidal rule. And basically what this is saying if we look at this, is we're taking heights. We're taking this width here, right? We're taking this width, and we're multiplying it by the average height of the start and the end, and then times the height of each of the middle ones. Okay, so the way that this works out is essentially all we're going to do is we're going to take, let me write it down here. So we're going to say the area equals the W times H1 plus Hn over 2 and plus H2 dot 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 all the way up to Hn minus 1. Okay, so the question is, what's n? I mean, that's once you know what n is, and you should be good. I mean, hopefully it's pretty obvious that this W here is 25, and the heights are going to be, you know, these different values here. That these are going to be our heights, right? So these are going to be our h's. So where do you start? I'm going to start with 1, 2, 3, 4, 5, 6, 7, right? I mean, that's kind of where I go with this. And when I plug this in, it's just going to equal to 25 feet times, again, the first one, which is going to be 145, plus the end one, which is going to be 146, all over 2, plus, and this is where I'm going to get kind of, maybe I'll use another color here, but I'm going to take all these middle ones here, right, these middle ones, and these are going to be at full force or full value here. So I'm going to take this times, 137 plus 131 plus 134 plus 147 plus 150. Okay. So once I have that, basically we're good. I mean, and really all that we're saying here is like the 145 over 2 is going to give us kind of the first half of this area, right? The 137 is going to give us kind of each, half of the area either side, and we're just going to keep moving on and get a total area here of, well, let's just double check. So I'm just going to plug this in just to double check, but what do I get? I get 25 times 145 over 2 plus 146 over 2 plus 137 plus 131 plus 134 plus 147 plus 150. Man, that's a lot of numbers. So don't screw it up. Sometimes it's easier just to like type it in twice, but if you get a number here that says 21,112.5 square feet, I didn't convert this one back to acres. You could convert it back to acres. We're going to get a value up here that works, that I'm happy with, and hopefully you're happy with as well. Okay, so this is the trapezoidal rule, right? So this is the trapezoidal rule, right? Trapezoidal rule. So the next question is, the same area, how does it change when we use Simpson's rule? Okay, so I just saw Austin. I just saw a comment on the prismoidal. Typically, the way I've seen it done is you're doing 3 stations at a time. So you're doing the first 3, then the next 3, the next 3, and if you're given more areas, I don't know. Maybe if you've seen something else like that, I don't know. To be honest with you, I'd have to look into that if there's another way to do it. But typically, you're just doing the 3 sections. Okay. So let's keep going here and go to the Simpson's 1/3 rule. So Simpson's 1/3 rule is a similar rule, but man, this just looks more complicated. It is a little bit more complicated. Actually, it's derived off of like a calculus-based approach and looking at like creating curves and integrating curves and doing all that sort of thing. So it is a little bit more complicated for sure, but it's not crazy more complicated. So let's take a look at what this looks like for this problem, see how it varies, right? And what we get. So let me come back to my sheet here, and what I'm going to get. I'm going to get this area, right? And this is Simpson's 1/3. Okay. So what this is going to be? This is going to be the area equals W times this big bracket H1. That's easy. And then it gets to be the summation. So plus the summation of, well, 2 times the summation of n minus 2 for k equals 3, 5, dot, dot, dot of h sub k. Okay, plus 4 times the summation of n minus 1 for k equal 2, comma 4, comma 6. So these are even values here of h sub k plus, h sub n. And you divide all that by R3. Right, so that gets divided by 3 to get the 1/3 in there. And again, the biggest question here is, what are the values, right? So if we write this out, 25 feet times h1. Well, what's h1? H1 is just going to be this 145. Okay, so h1 is going to be the 145. Hn is going to be 146. Makes sense? If we take a look at and number these again, we're going to say 1, 2, 3, 4, 5, 6, 7. So we're going to have these 7 different points here. And h1, we're going to say 145 plus 2 times what? This is just, we have to figure out what to add in. So we're going to add in 3, right? I mean, if we think of it like this, these are going to be the 3 value. And let me highlight it like this. This is going to be the 3 value, okay, and the 5 value, and there's the 7 value goes to the next side. So we're going to add in 131 feet and 147 feet. Okay, so we're just taking the odd ones, not including the start and the end. Okay, and then let me do another color here, but I'm just going to take this version here, right, and now we're going to take the even ones. So I'm going to take 2, 4, and 6. And I'm just going to take those ones and multiply them by 4. So 4 times, what, 137, 134, and 150. Okay. And then I can't forget my 146 here, which is the end. All right, that's the other, that's h7, right? And I'm going to divide all that by 3 and get an answer. Okay. So it's a little bit more computationally intensive. It's a little bit scarier to look at, because it has these summations in it, okay, but it's not super crazy when you do it all out. The value that I got here, and maybe hopefully you get the same value, but the value that I got was 21,09167. So 21,091.67 square feet. Which is different, right? It's a little bit different. It's a different estimation than the trapezoidal rule. It still works, right? It still gets us really close to the same value. Okay, so how would this really be done in the field? In CAD. Okay, so I mean, what can I say? I mean, if you need to do a quick hand calc, you could do something like this. Personally, I would never use Simpson's rule just on a hand calc to check something. I'd probably use the trapezoidal rule just because it's a little bit simpler. You don't have these summations. This one's actually a little bit more accurate, but again, it's like it's what, 20 square feet on 20,000, so it's not making a huge difference. Okay. So either way, I wanted to show you how these formulas work in case you get a specific question on Simpson's rule or trapezoidal rule. They hopefully shouldn't be a mystery. They should be fairly easy points that you can get. So one thing to point out is Simpson's rule: n must be odd. Okay, so n, the total number of heights that you have here. So if we're looking at this, the total number of these heights, you must end in an odd number. If it doesn't, you have to revise it somehow so that you can get an odd number. All right, so not too crazy, but something that's worth taking a look at. So let's go to question number 10. So question number 10, I actually started out, I think I revised this question like 2 or 3 times before I finally got down to this version of it. But one of the things that you might be doing is you might be having either a fill pit or a fill stockpile that you need to get a rough estimate of yardage on, right? So how much material is needed to fill this pit, how much, or if this was a mound, of fill, a stockpile, how much fill is in there. You could take some quick level measurements just around it on a grid to kind of figure out what that might look like. And that's all this is, right? So what this is, you know, maybe we have a pit that's 50 feet wide. It's, you know, has some dimensions here. But we just went around with a level, took some shots, got some rough ideas of how, you know, how deep this is in different spots and how much fill we might need to fill this, right? This is a borrow hole that we dug out of, and we need to fill it back in. So just this isn't getting into expansion, you know, it's not getting into swell, shrink, and all that stuff. This is just saying straight up fill. Okay, and could I write this question better so that it had, you know, this shrink and swell and soil in there? I probably could, but it doesn't say anything about that, so we're not gonna worry about it. But in order to do something like this, one of the things that, I mean, this is just kind of, again, one of those things that's not in the handbook, but it's one of those things that when I was teaching surveying, I actually taught, because it's kind of a basic kind of concept, but it's a volume by area, and it's, you know, and average depth. Okay, so all that we're going to do here is we're just going to take two areas. I'm going to call this like area 1 and this area 2. Okay, and it's basically what I'm going to do is I'm just going to, you know, I'm just going to make a table. So I'm going to say, you know, the block, the area. So I've got area 1 here. I've got area 2. Right, what's my area of area 1? Well, it's just going to be 50 feet. That's this width over here, right? That's the 50-foot width, times the average height of 25 feet plus 50 feet over 2. So on one side, it's 25 feet. On the other side, it's 50 feet. Okay, so this is going to be my area of that section. So when I do that, I get, you know, what do I get? I get 50. 50 times 25 plus 50 and parentheses over 2, I get like 1875. So 1875 square feet. Okay, and then if I go to area 2, this one's a little bit easier. I got 50 feet and 50 feet. This typical just means typical. It means that it's the same dimension, kind of, unless stated otherwise. So 50 feet times 50 feet. That one's a little bit easier, and I think it should be 2,500 square feet. And I'm just going to do average depth here, right? So the average depth is what? Well, basically all I'm going to do is I'm going to add these up. So 0.6 plus 1.4 plus 2.1 plus 3.6 divided by 4. What's the average depth? It's not really rocket science here. This is just kind of a quick estimate of, what do we get? 0.6 plus 1.4 plus 2.1 plus 3.6. And I take all that divided by 4, and I got like 3.85. So I think if I'm looking at that right, did I get 3.85? Did I do something wrong? Unless maybe I did something wrong. Did I type something in wrong? Oh, I divided it by 2 on my calculator. That doesn't work. There we go. Because it was different than my notes, and that's always scary. But 1.925 feet, right? And where does that come from? I could have written that out, but this just comes from, right, 0.6 feet plus 1.4 feet plus 2.1 feet plus 3.6 feet all over 4, right? That's just the average depth. And if we do the same thing for the you know, 0.2 here, block 2, right, what do we get? We get, let me see if I can do this right the first time. 3.6 plus 2.1 plus 1.8 plus 1.4 and divide it all by 4, and I got like 2.225. You know, and again, is this perfect? By no means is this perfect, but it's just an estimate. It's a quick estimate, and I can get an average, you know, volume here of, what do I get? I get, just multiply these two, and I get, you know, 1875 times 1.925. I get about 3609 cubic feet, which if I divide that by 27, I get about 130, you know, 134, roughly 133.7 cubic yards. And these measurements aren't super precise anyway, so it's going to be plus or minus. But if I do the next one, 2,500 times 2.225, I get like 5562.5 cubic feet, which is, if I divide that by 27. I'm going to get like 206, you know, 0.0 essentially cubic yards. Okay, so if I add those up, I'm going to get my total volume here of about essentially 340 cubic yards. Okay, so just kind of a basic idea here, but you know, sometimes you're going to get things that aren't exactly in the reference handbook, but hopefully it's not too much of a stretch, right? I mean, this is kind of like looking at a trapezoid in 3 dimensions. It's like just looking at that average height, but now we're looking at average volume, so we're taking, you know, the area times the average height of the whole you know, square or grid block that we have in here. And it's not too crazy, right? I mean, it's not too crazy, and hopefully the concept's not way far out there. So I don't know, maybe it makes sense, maybe it doesn't, but let's keep going. So question 11 puts us into part D here for coordinate systems, and I kind of struggled with questions for these for a little bit, because I was trying to think, like, coordinate systems, the way that I've used coordinate systems have been with orthoimagery, have been with, you know, using RTK surveying to go find GPS points to come up with a state plane projection so that we could, you know, georeference a map. And maybe I just spoke in like foreign language to you, but like what I've used the coordinate systems for, I mean, it goes beyond kind of the basics of latitude and longitude. Hopefully you learned your basic latitude and longitude in you know, in your geography class whenever you took in high school or wherever. But I mean, latitude and longitude are kind of one of those basic things where when you start looking at the USGS, you start looking at some of the structural pieces where you're looking to locate specific parameters at specific points. They're typically in some GIS database, and you typically need to know like a latitude and a longitude in order to get those. Most of the time now there's maps, so you can just plug in a point on a map, and you don't actually have to know the specific coordinates. Google Earth is great in terms of getting coordinates if you need coordinates. It's free, it's available, it's easy to use to get coordinates. But just this idea, again, with what coordinates are being used, what coordinates are being plugged in, I threw this one on there just to kind of get you thinking. The idea here is we have latitude and longitude lines that divide up the world, right? So these are kind of where you start, right? I mean, we have the equator, we've got different points here. We have New York State, so the great state of New York. So maybe you don't think New York's that great, but you know, it's where I live. So I can't, and I don't live in the city. So some of you love the city. I'm not a huge city person. I've lived upstate where you know, we walk on our road and there's cows, but that's the way it goes. You know, it's fun. So what do we live? You know, I'm up here somewhere in New York, right? And is that a good spot for New York? New York's probably a little bit further over. You know, maybe in there. I don't know. Let's look. So where is this? This is maybe somewhere in New England. I don't know. But basically what I'm saying is, what's the latitude and longitude? So let me just highlight some lines. We've got this line here, which is a 30-degree line. We've got this line here, which is a 60-degree line. We've got 60 degrees coming down. We've got 90 degrees coming down here, right? So where are we? Well, we're kind of halfway between 30 and 60, which would mean we're somewhere going to be probably in this 43 range, right? We're kind of halfway between 40 and 30 and 60, and we're kind of halfway between 60 and, don't screw this up, this isn't 120, this is actually 90, so not all of them are labeled. You know, is something this easy going to be on the test? Probably not, but I wanted to introduce this just because the geographic coordinate system of latitude and longitude is like the most basic. And then it gets more complicated. But where are we? We're kind of halfway between the 60 and 90, so that's going to put us, I would say, like 43, 75. Okay, so north, 43 degrees north, 75 degrees west, right? So this is your latitude and your longitude, and this is where the other thing that it gets screwy sometimes is normally we think of X and Y, but a lot of times in surveying we're northing and easting, or northing and, in this case westing, west of the prime meridian. Okay, so it's kind of a simple idea here, but it translates, and the reason I put that in is because it translates kind of to this idea of coordinate systems and specifically like state planes. So one of the things that you'll probably see at some point in your civil engineering career are you know, GIS ortho reference images, right? So, or you know, GIS reference base maps where you have control points that reference some state plane coordinate system. And the nice thing about state plane coordinate systems is it takes this three-dimensional map and turns it into like a rectangular Cartesian grid, right? So we like working in two dimensions. We like thinking in 2 dimensions. We like measuring in 2 dimensions because it's a lot easier than dealing with the 3 dimensions. So the state plane coordinate system, what it does is it takes that globe, and it looks at some projection. It's a cylindrical projection, either vertical or horizontal, and it basically takes that, you know, cylinder and sticks it over a certain area of each state, right? And within the states themselves, there's a bunch of different projections. So what happens is you get this projection that we take this cylinder, and it's kind of like taking this cylinder, you know, putting it over the globe, and then laying it flat and saying, okay, that's going to be our state plane coordinate system, right? So we have this cylinder that we wrap over the globe. But what do you notice? Well, you notice that as you get farther away from the center of that point, or the center of that projection, you're going to get farther away in terms of accuracy. So these state plane coordinate systems are set up for kind of narrow parts of the state. They're not like super narrow, but they're you know, in New York, I think we got an east, a west, a central, you know, so we've got a number of different state plane coordinate systems, but they're beneficial because they allow us to take that three-dimensional kind of curved map and break it into a flat plane system. So, you know, we can reference with a pretty high degree of accuracy a certain point and kind of have a pretty good idea of where we are. GPS isn't perfect in terms of sometimes if you're in trees, or you can lose signal and it can get annoying and from that sense, but there are some ways where you can do RTK surveying where you can tie into some known control points and get really, really high precision. So it is useful. I wanted to bring it up here. I didn't have like a great problem because I was trying to, I mean, getting into GIS can be kind of a topic. I don't know, maybe you took a GIS course. We encourage our students to take a GIS course, but maybe you didn't take it. I don't know. So basically where I'm going here is let's select all the benefits of a state plane coordinate system. That's just to get us talking about this a little bit with coordinate systems. So kind of the way I was explaining this was they do use the cylindrical projections of the Earth to establish a plane or flat surface for mapping, right? So it takes that, it takes the round Earth, it kind of puts over this cylinder, and then it lays like just a certain little section of that cylinder flat, if that makes sense. But it's only good for a little, I say a state area. It's not like you're not going to do the whole country with the same state plane coordinate system, right? Does this eliminate mapping errors related to the curvature of Earth? No, it doesn't eliminate mapping errors. It actually introduces mapping errors because it takes a curved surface and it makes it flat. So this actually introduces mapping errors and it doesn't eliminate them. Okay, so that's not a good one. But as we keep going here, it is adopted by many local municipalities. So they'll have certain benchmarks or points that you can reference. They'll ask for certain documents to be submitted with a certain state plane coordinate system, something that should be used. They are both in feet and meters, so you can get, you know, NAD 83 in feet, you know, or in meters. You can get both depending on what your system you're working in. They are not good for national mapping, right? So they're not intended for national mapping in terms of you're not going to use the same state plane coordinates for the whole, like if you're doing a multi-state project, like, you know, a big pipeline that goes through multiple states, you're not going to use the same state plane coordinates for that whole project. You're going to have to break it up into chunks. Okay, so they're not intended to have one projection for the whole country, right? It doesn't work that way. You get too much error. But it does convert kind of this geographic latitude and longitude into these northern and easting values that we can use when we're laying out a site. So that last one I will highlight as a good one as well. Okay, so again, more of a concept question. Maybe this is one of those alternative question types, but the idea of coordinate systems, typically we're looking at those northings, eastings. We saw some of that earlier as well, but I also wanted to throw in that GIS piece of it into the review in case you get some concept question on that. All right, so hopefully that helps, and we're moving right along. So the last couple questions here get into leveling, and I had another question here, but it was kind of redundant, so I just started back with this one. But this is kind of a typical benchmark survey run. I didn't close this one. I just said, if you're given this run, what's the elevation benchmark to? And this is one of those things where if you haven't done surveying in a while, or maybe you've never done surveying, all that we're doing here is we're setting up a level, right? We're setting up a level here that can take a horizontal, it basically cuts a horizontal plane. And we're taking a measurement back to a known point. So we're putting a rod or a staff, a level staff, on a known point. And we're measuring the distance from that known point to establish what? To establish the height of the instrument. Once we know the height of the instrument, we can take a second reading, we can take a foresight reading, and we can take a reading to another point here, which is going to be like a turning point. And then we're going to move, and once we know a new point, we're going to move and just kind of keep repeating this process of taking measurements on a level plane to kind of figure out where we're going. So if you don't remember the surveying notes, I'm going to write them down here, but basically you have your point, right? You have your back sight, and anytime I'm writing back sight, I like to write the plus in there. When I was teaching surveying, that's the way I would do it. You have the height of the instrument and the foresight. Okay. So the backsight's looking backwards, the foresight's looking forward. The height of the instrument's kind of this level of the instrument that you have to figure out. And then we're going to come up with our elevation. Okay, so these are the different points. Sometimes you'll have a notes section over here. If you're setting up a surveying notebook, these are the things that you're going to put in, right? So, we're going to backsight to benchmark 1. And the backsight we have is 1.25 feet. We know the beginning elevation of that benchmark is 511.15. Okay, so what happens is we add the 1.25 to the 511.115, right? So 511.15 plus 1.25 is going to give us a height of an instrument of 512.4 feet. Does that make sense? So the height of this instrument here is 512.4. Okay, but then we're going to set up at turning point 1, or I'm sorry, we're gonna take a I shouldn't say we're going to set up at turning point 1. Then we're going to set up kind of at this next point here. We're going to set up at this point here, and we're going to backsight now to turning point 1. Actually, before we backsight to turning point 1, we have to foresight to turning point 1. So we're going to foresight to turning point 1, and that's going to be a foresight of 6.14 feet. So why do I care about 6.14 feet? Because if I subtract the 6.14, right? If I subtract the 6.14 from 512.4, that's going to give me the height at this point. Does that make sense? So 512.4 minus 6.14 is going to give me the height of 506.26. Does that make sense? So then we're just going to kind of repeat this process, and I'm just going to keep writing these in. I'm going to put turning point 2 here. I'm going to put we have the benchmark, but basically we're going to have the turning point 2. We're going to have benchmark 2, right? So we're going to have our backsight of 2.34, our foresight to turning point 2 of 1.96. Our backsight to turning point 2 is going to be 0.56. Our foresight to the benchmark is going to be 1.33. And honestly, you don't need to write all of these down, especially if you get a problem like this. You don't have to write all of them down. I kind of like to write them down just for completeness here. And once you get the first one in, it's not too crazy, because we go from 506 and we're going to add the 2.34 to get back to the height of the instrument here. So 506 plus 2.34 is going to give us 508.6. Sorry, moving all over the place here. And then we're going to subtract off, right? We subtract off to get our new elevation. So 508.6 minus 1.96 is going to give us 506.26. 0.64. We're going to add the 0.56. We have 507.2, and then we're going to subtract off 1.33, and I got 505.87 feet. Okay, so when we're all said and done, that's the elevation of this benchmark. Okay, so kind of the basics of differential leveling. Hopefully, even if you don't remember this whole, the whole surveying note piece of it, hopefully just intuitively you can figure this out, right? You add one, you subtract the other, you add one, you subtract the other, you add one, subtract the other, and you kind of just keep working your way across until you finally get to the point that you're hoping to get to. Okay, so kind of hopefully that's fairly straightforward, nothing too crazy. And now we're on the last question, and man, this session's going quick, which is you're probably like happy about. I mean, like, man, some of these sessions have been slogs, but this one it's going a little bit quicker. Hopefully that's a good thing. But let's look here. We got 2 points we're taking using a total station and a prism pole. So in addition to basic differential leveling, where you just have levels, right? You can use a total station that measures angles and distances. And typically, in the version that we're doing here, we're measuring a slope distance and a zenith angle and a horizontal angle. Okay, so slope distance, the zenith angle, and the horizontal angle on the plane. Okay, so what does that look like here? Well, we set up our total station at a point, we back sight to a benchmark, and then we take kind of a foresight to another point. Well, what's the elevation at this point, right? Can we figure that out? And hopefully, even if you never use a total station, you don't even know what a total station is, you can still figure this out. But a total station just measures, distances and angles. Okay, so hopefully we can figure this out. But let's draw another. Let's make this diagram a little bit bigger here to try to figure that out. But if we have our total station, our total station here. Okay, so this is our total station, and we're gonna measure with that total station. What we're going to do is we're going to measure kind of back to our prism pole at one point, and we're going to measure forward to our prism pole at another point. Okay, so what does this look like? It looks like we're going to make this measurement, and we're going to make this measurement. And what angles do we have? Well, the angles that we're told that we have are 88 degrees, 17 minutes. There's that degrees, minutes, second thing again. And then this angle is going to be 92 degrees, 46 minutes, degrees, minutes, seconds again. Okay, so how does that work here? Well, what we have to do is we have to make sure that we convert our angles. So let's just do that quickly, right? So if we convert our angles, I'm going to just use math, DMS, degrees, put in 88 degrees, then the 17 math, DMS, minutes. So once I have got 88 degrees, 17 minutes in my calculator, I hit enter, and I get 88.2833 degrees. Okay, and similarly, I could do the same thing for the 92.46, right? So 92.46, that's going to give me 92.7667 degrees. Okay, so that's the least of our worries. So we also know this slope distance is going to be 61.25 feet. This slope distance is going to be 58.45 feet. And what do we do with this prism pole, right? So we got this prism pole. Essentially, we can kind of ignore it. That's what I like to do. Is kind of just ignore it, because we added on one side, we subtracted on the other. Okay, so the idea is we're just going to call kind of, even though this benchmark is really 518.30, we could get this point, plus 4.75, and then get this point, and then subtract 4.75. But if we're using the same prism pole and haven't really changed anything, we can kind of ignore it. Okay, so what I'm going to do here next is I'm just going to have to figure out some basic trig. So we started with basic trig, we're going to end with some basic trig. Right, but what am I looking at? If this is my height of the instrument, right, what do I need? Essentially, I need two heights, right? I need this height 1 and I need this height 2. If I can get those two heights, I know that my final height is just going to be my 518.30 minus h1 minus h2. So let's use some basic trig here, right? If we know this angle is 88.2833, I can do this a couple ways. I can find this angle here and this angle here, right? I mean this shouldn't be too crazy. This angle is going to be the easy one, 2.7667 degrees. You see it? And what's this one? Well, it's going to be 90 minus 88 90 minus 88.2833. And if I do that correctly in my calculator, I'm going to get about 1.7167 degrees. Okay. Once we have that, what do we need? All that we need to know is the sine of 1.7167 degrees equals what? The opposite over the hypotenuse. In this case, it's going to be the slope distance. So h1 over the slope distance. So what does that mean? It means h1 equals the slope distance of 61.25 feet times the sine of 1.7167 degrees. And h1 is going to equal, let's see if I did it right, 61.25 times the sine of 1.7617, and I get about 1.835 feet. So I'm just going to keep an extra decimal place there for now at 1.835 feet. Okay. And we can do kind of the same thing over here. We can say the sine of 2.7667 degrees equals what? h2 over this slope distance. Maybe I'll call it slope distance 2 and this slope distance 1. Okay. And we can get the same kind of thing here. h2 equals 58.45 feet times the sine of 2.7667 degrees. And h2 is going to equal, let me see if I get this right, 58.45 times the sine of that, times the sine of, I got to make sure I get my angle in here right, but what I 2.76667. So I got about 2.82 feet. Does that sound about right? 2.82 feet. So if we know that we're going from 518.30 feet, again, I could add the prism pole of 4.75 feet and then subtract the prism pole of 4.75 feet, or you can just leave that out. And then what I'm going to do, I'm going to also come back in here, and I'm going to subtract 1.8, let's say 884 feet minus 2.82 feet. And I don't know how I rounded this, but let's see if I rounded it right. So 518.30 minus 1.84 minus 2.82, it gets us to 5. Honestly, I think these questions, whether it's angles, distances, trig, area, computations, earthwork volumes, the coordinate systems, right, differential elevations, leveling, basic leveling, you should be able to do. We did talk about percent grades in some of the other sessions here, but hopefully it makes sense. And I don't know, maybe questions, maybe you don't, but if you don't and you're still hanging on, got a joke. My wife gave me this joke, and it's I think this came from her grandpa. God bless him, he's 100 years old and he's still married. I mean, he's one of those people, I think they've been married almost 80 years, like he and his wife. And they're both 100 and they're still living and they're still with it, but he loves jokes, so he sent this one over. So this is a tribute to him. A man had 12 children, was having trouble finding a house to rent. You might understand why he was having trouble to find a house, because he had 12 kids, but people did not want to rent to him as they felt the children would destroy the place. He couldn't say he had no children because he didn't want to lie. I mean, we're going to do ethics in a couple weeks here, so he can't just lie, right? So he sent his wife and 11 of the children for a walk in the cemetery. He went with one child to the real estate agent. He found a house he loved, and the price was right. The real estate agent asked the man how many children he had. He answered 12. Where are the others? The agent asked. He said. The man put on a sad face and answered, they're in the cemetery with their mother. Well, he got the house. So, thanks, Grandpa. You know, I mean, it's a good one. I don't know. Maybe it made you laugh. Maybe you would just laugh if there's another joke out there. It goes, there were 4 surveyors working on the side of the road. And the joke just ends there because they were working. They were, you know, you see surveyors and you think, man, they're just standing around. But then you realize you're standing around in the cold and the rain and all these things, and they've got a lot of hard work to do. So we appreciate our surveyors. We appreciate that they do a good job. So hey, that's it for tonight. If you got questions, feel free to drop more comments. If this has helped you, hopefully it helps you push you along to go past that FE and to do some great things with your degree and with the rest of your life. So I wish you the best, and next week I think we'll be doing dynamics, so that should be fun. Look for some questions on dynamics, and we'll round it out with some ethics, some engineering economics, and hopefully these review sessions have been helpful. So hey, thanks for showing up today. It wouldn't be as much fun without you. And until next time, hey, keep working hard and moving onward and upward.